And this is one of the common mistakes people make. With the given standard deviation, that is the population standard deviation. So that is if I was looking at every single person in the population. However, when you take a sample, that population standard deviation is altered because you're not looking at everybody, you're looking at a subset, a small group of the population. And so what we have to do is we have to go in and we have to take that population standard deviation and we have to divide it by the square root of n. So biggest mistake that I see is people read the question and they say the population or the standard deviation is 2, and then they just use 2, but they don't take into consideration what sample size they were actually using. So for conditions, we have to go in and make sure we have random selection or random assignment. I will say, because I know it's going to be not a ton of writing, but more writing than you're probably wanting to do this early morning. With the 2 conditions that we always check, they're the same as they've always been. So if you know how to check for mean and how to check for standard deviation, you don't have to write it every single time I do. But for 10% condition, n needs to be less than 10% of the population size. Now, the other option is you could go in and say that they are independent for experiments. Typically, that's the only time we really want to say it, but those 2 conditions, not new, same exact thing, not changing. Now, for the shape, we want the shape to be approximately normal. So the sampling distribution of x bar to be approximately normal. And to check that, we kind of have 2 options. If n is less than 30, then the population distribution is normal. It has to be normal. Otherwise, this does not work out. And if n is greater than or equal to 30, CLT is going to apply. And therefore, we can say the population is, or the sampling distribution is approximately normal. So we will kind of see both of those methods today. I'll show you one where they tell me in the question it's normal, and I'll show you one where we have to actually check central limit theorem. The only note I will make is whenever we're doing proportions, they do not care that you say large counts. You don't have to say large counts. However, when it comes to means and you are saying n is greater than or equal to 30, you have to mention central limit theorem. I want to say that the reasoning is large counts has a lot of work. It shows that you have successes and fails, and it's kind of proving that it's a normal distribution eventually. If you just have n is greater, like 20 is greater than, or not 20 is greater than 30, 50 is greater than 30 on your paper, and that's it. Like, yes, that's a true statement, but what is it coming from? What does it represent? So that's my guess as to why they require you say CLT. But it is required, so we will say it when we actually write this out. So let's go in. I try my very best, and I try to do this in 5, 6, 7, and 8, all of those units, to kind of keep things exactly the same. I know that can be confusing for some people because you want some type of differentiation. However, I think having the same steps makes it a little bit easier to remember all of the steps. So we have the same 4 steps that we did when we were doing proportions. The only difference is we are now dealing with means. A lot of the time on the question itself, I like to come in and I like to kind of identify what am I looking at. So suppose the heights of young women are normally distributed.
I sincerely apologize for the interruption, 20 minutes into class, but it's important that I share a couple of things with our students real quick, and we'll share this throughout the day. But students, just want to remind you about our technology policy. I think we're all aware of the sweeps are. I will let you know that tardy sweeps are going.
It's still slow. It's not slow during first period. I don't know why specifically during second period, because I paid attention yesterday.
Visit a tardy station that is manned by administration. On-the-spot consequences or warnings will be given at that time.
Ooh, that is not how you spell mean.
We don't like rules. Rules are often broken, but I just want to make this announcement and ask our student body to please partner with us on those two things, as they are becoming huge issues and our sweeps will begin soon. I appreciate you guys helping us out and adjusting to that, and more information will be shared throughout the day. Thank you.
So when reading this question, I notice first they're giving me numbers. So they don't say 25% of people like dogs. They don't say 25 out of 100 people like dogs. They tell me the mean is this and the standard deviation is this. Immediately, I usually say, if you read a question and you notice it's giving you a standard deviation, that is a big sign that you are doing means and not proportions. So once I know it's a means, I'm then identifying, is it a one population or a two population? Two populations, you just have to check both populations for the conditions. But in this case, we just have women. So I'm going to define my parameter. And you probably noticed I changed my symbol. It's no longer P. And I know we've been writing P for like days at this point, but it is always going to be mu when it comes to a population mean. So I use the mu. And then I have to come in and kind of identify what am I actually trying to find. I want to find if the mean height is greater than 65 inches. So that's coming in and taking X bar and seeing, is it bigger than 65? And that's kind of what I'm trying to calculate. When I actually grade your tests, if you got your FRQ back today from last class, I had a check for, did you do this? And did you write the Z-score way of writing this? I don't necessarily require both because College Board doesn't require both. As long as one is there, that's showing direction, and that's kind of what they're looking for. However, I do think it's really helpful to have that, because by the time you get through your conditions, you haven't even thought about what am I actually answering. So if you can read the question and immediately go in and think, okay, this is what I need to find in the end, that is going to be the most helpful. So now I'm going to go in. It's kind of like your plan. Random. They are taking an SRS of 10 young women. And this should feel familiar. This is no different than what we did for proportions. So I can say mu of X bar is equal to 64.5. So the mean of the sampling distribution is going to be equal to the population. Now, for the next condition, we have normal. And you can write these in any order. I know I've mentioned that before, but sometimes I'll do independence first, normal, it does not matter. For the normal condition, they tell us that the population is normally distributed. So I'm going to say population is normal. And therefore, that kind of tells me that the sampling distribution of X bar is approximately normal. If the question had said it was skewed to the left and their sample size is as small as it is, then I cannot say that this is a normal distribution and that condition would fail. But because they tell me the population is normal, the sampling distribution also will be normal. And then we have our independence. And that is going to tell me that I have my 10% condition. So I'm going to say my sample size of 10 is less than 10% of all young women, which seems reasonable enough. That seems safe to assume. One way of making sure that you know it's safe to assume, take your sample size, multiply it by 10. If that number seems big enough, like the population is bigger than that, great, it passes. most of the time it's going to pass. The only time I would say that it fails is if in the question they tell you the population size is 500 and then you check 10% condition and it's something like you need to have 3,000 people. And that would be something where it's going to fail. Now, the standard deviation formula does look slightly different from what we did for proportion, so I went ahead and rewrote it just so you can see where these kind of setup is coming from. My given standard deviation is 2.5. My sample size is 10. So that means my standard deviation for this sampling distribution, because remember, each sample size has its own sampling distribution, is 0.7906. And from here, everything is the same. We have a mean, we have a standard deviation. I'm going to first calculate a z-score, and then I'm going to plug that into normal CDF, and then I'm going to get my probability and write my conclusion sentence. So ideally, if you felt pretty good about proportions, this should not be a ton of new information. It shouldn't be much harder. First thing, we're going to calculate the z-score. If you need some point of reference, the formula that I fill in is taking our claim, whatever we're trying to figure out, subtracting the mean and dividing by standard deviation. So value minus mean over standard deviation. So that is going to give me 65 minus 64.5 all over 0.7906. And that gives me a z-score of 0.6324. Now, we've gone through the steps of normal CDF multiple times at this point. So because we have a little bit of a longer set of notes, I'm just going to kind of give you the normal setup that we have. The reason why I like to write that original statement is I go in and I just write exactly what I wrote, or not 65, exactly what I wrote in the same inequality direction from the very beginning. It's just instead of using 65, I'm now going to use my 6.6324. So then I'm going to have normal CDF. And I'm going to have lower is, and because I want everything greater than 65, my lower is going to be my z-score. My upper is going to be positive infinity. My mean is 0, standard deviation is 1, and so this gives me 0.2636. And once you have your probability, you just repeat the question and plug in your answer. So I'm going to say the probability that the mean height of an SRS of 10 young women is greater than 65 inches is approximately, and you can use the decimal or the percentage. I'm going to go, I've been doing the decimal so far, so I'll just do decimal today. Approximately 0.2636. Now, bless you, I'm going to do one more FRQ for one population just so that we don't have to double up on conditions if we need. With a question like this, where if you have this on a test, it's not going to have all of the boxes. It's not going to say step 1, step 2, step 3, step 4. The general idea is you have to write a conclusion sentence. You are answering their question with a sentence. Anytime you are on the AP exam, that is going to be your go-to. However, there are some times, and I would say the likelihood of this being an FRQ on the exam is really low, but there are times where they can ask you questions in parts, and these parts require multiple different calculations. In those cases, a summary sentence isn't always necessary. Now, can you do it? Sure. But the reason why they require sentences for these types of questions is because you are doing one thing. Yes, it's multiple steps, and yes, it takes some work to get there, but you're only finding one probability. If you read a question and you find that they're asking you to do multiple things, a lot of the time the grading rubric does not reflect needing interpretation sentences for those because they know you're putting in a little bit more work to get each of those individual values. So whenever it comes to example 2, they have a restaurant is suspected of undercooking its burgers. The restaurant claims that its burgers are cooked to medium doneness with an average internal temperature of 160 degrees Fahrenheit. Immediately seeing average and seeing a quantitative, like population parameter, that tells me we're dealing with means. And then in a standard deviation of 5 degrees Fahrenheit. For the questions that follow, assume the restaurant's claim is accurate and that the distribution is a normal distribution. So one thing, I don't see any mention of a second restaurant or a second location or anything like that. So anytime I just see one thing, we're dealing with one population. Now, for the first question, what is the probability that a single randomly selected burger? So this particular question is not taking an average. It's not taking a sample and taking a group and finding the average and reporting that number. So really, this is just a variable X. It's not an X bar. It's just one thing on its own. So what we would actually do is we take an approach similar to what we did when we started this off in like unit 1. We're going to say the probability that X is less than or equal to 158. Now, with this particular calculation, when I go in to find my z-score, I'm not going to need to use the formulas that we just kind of were talking about because it's only one. So I'm going to take 158 minus the average temperature of 160, and these are coming directly from the question, and divide it by my standard deviation of 5, and that's going to give me negative 0.4. So I'm actually taking the probability of z being less than or equal to negative 0.4. One little note. Say, for instance, you're like, okay, I didn't realize it was a single burger, and I still use the formula. The mean isn't going to change. It's still 160 even for the sampling distribution. But if you think of the sample size, it's 1. So even if you took the square root over, or the standard deviation over the square root of n, the square root of 1 is 1. So if you're dividing by 1, that's not going to change the standard deviation. Now, what would probably lose points is the x, if you used x bar instead of x. Thinking of if this were an AP exam question, but if you went straight to z, it wouldn't make a huge deal. So we have normal CDF. Lower in this case is negative infinity. Upper in this case is negative 0.4, mean of 0, standard deviation of 1. And this is 3, 4, 4, 6. And I'm not going to write a sentence because I am going to do multiple calculations. One of the recommendations we make whenever we get to AP prep and AP review is read the entire question. Before you start working, read every single part, try to process and kind of make a little note as to like what you think you should be doing so that you don't do a ton of extra work when you don't have to. So for part B, a secret shopper comes in. They are going to take an SRS of 25 burgers and calculate the sample mean. What is the mean and standard deviation of the resulting sampling distribution? So all I'm doing is I'm going to find mu of x bar and standard deviation of x bar. They told me that this was a normal distribution. However, if you're just asked to find a mean and standard deviation, you can just use the formulas. You don't have to check the conditions. The only time the conditions are important is when you go to calculate a probability. When you're going and you're actually using these to make a normal distribution to find a probability, those conditions need to be there. Now for this, we're just finding the numbers, so we don't have to do anything. So 160 degrees Fahrenheit And if I wanted to find the standard deviation, I would take the value that they gave me and divide it by the sample size. And so square root of 25 is 5. And so 5 divided by 5 is 1. Hello. Hi. Can I help you? This is a high school. I have not called anybody. I'm sorry. I have not called. Do you have a student here at Richardson High School? Richardson High School? Okay, then I don't think I called you. I'm sorry. Whoever watches this video is going to have a very fun time of like all of the random distractions. They're like, somebody called this number. I was like, I did not. Not me. They don't have a student here, so it wasn't me. Okay, 1 degree Fahrenheit. Sorry, friend. This is why I don't answer calls that don't say Richardson High School. Now, the actual calculation for the probability, they said they have a sample mean of 158. They want to know, what is the probability of getting that? What is the probability of getting 158 degrees or less? So with the 158 degrees or less, I would have to go in, and they tell us to assume all conditions are met, so we don't even have to check the conditions. I'm trying to go in and see the probability that their sample mean is going to be less than or equal to 158. So I'm going to go in, 158 minus 160 divided by 1, negative 2, z less than or equal to negative 2, and then I go in and I calculate the probability. And there's going to be kind of a point to this in just a second. Normal CDF, lower negative infinity, upper negative 2, mean of 0, standard deviation of 1. And this is going to give me a much smaller probability than part A, and we're going to get 0.0228. Now, that is a big difference between what we had found for part A. For a single burger to be less than 158 degrees, it was 35% chance it could happen. And then when I go to a sample being less than 158 degrees, there's like a 2% chance of it happening. And so part D is kind of asking the question, why do we think that happens? So the first thing I'm going to kind of point out, because I know some people are visual and this is going to help those people who need to see it. If I kind of look at part A and I were to draw out my normal distribution, it's going to center at 160. And I really only care about the left side because I'm doing less than. I have a 155, a 150, a 145, because this is the standard deviation is 5. So it adds 5 to the right and subtracts 5 from the left. And so the goal of that question was to find the probability that it's 158 degrees or less. So that would be something like around here and shading everything below. Now, that's a big area. But then if I come in and I look at what we did in part C, same kind of approach. I'm going to draw a normal distribution and I'm going to center it at 160. But this time, when I go in to draw out my standard deviation, the standard deviation changed. It's no longer 5, it's 1. And so when I go to shade everything under 158 degrees, that area noticeably shrinks. Now, if you remember back to 68, 95, 99.7, my picture is not to scale. But that area is drastically different because most of your area is within one standard deviation. So what you should notice is that standard deviation had a really large effect on our probability changing. So one little kind of summary sentence we can say is part C has a smaller standard deviation. Therefore, the probability becomes smaller too. And the reason why is the smaller your standard deviation, that is a direct result from you taking an average. So the larger sample size you have, and this is just a note, not a part of the answer, larger sample size leads to a smaller standard deviation, variability, spread, whatever you want to refer to it as. It gives you a smaller spread overall. If I went around the room and I asked everybody, how long is your drive to school? And I got a bunch of different answers. I could have people who say like 5 minutes. I could have people who say 45 minutes. And that's going to be a big spread of data because I take everyone as an individual value. That's a big sampling distribution. But if I go around the room and I ask 5 people at a time, and from those 5 people, I take an average, those averages are going to be a lot closer together. And so that causes that smaller spread. So larger sample size will always lead to a smaller spread. Now, last thing, and here's my repeat of if you know how to check for 10% and you know how to find a mean, then you don't have to write it down. We have 2 samples, x1 bar, x2 bar. 2 of the conditions are identical to what we do. I'm going to fill in kind of what we have. Approximately normal is my shape. My center is going to be x1 bar minus x2 bar is equal to mu1 minus mu2. And standard deviation, x1 bar minus x2 bar is equal to the square root. Make sure I write all my numbers. And these formulas, very much like proportions and the single populations and double populations, they are all on your formula chart. So I could make you go through and talk about how these are still using that combining random variable formula. But at the end of the day, it's on your paper. So you don't actually have to prove it or find it or create it yourself. You have these values. And I'll show you what the formula chart looks like so you can kind of have an idea of what you'll get. So I have my mean, I have my standard deviation. So for my conditions, the same exact things apply, but for both populations. So my N1 needs to be greater than or equal to 30. My N2 needs to be greater than or equal to 30. And if both of those things are true, CLT is going to apply, or both populations distributions, hello, are normal. Thank you. For the mean, you need to have random selection or random assignment. And again, the big thing is for both. And the last one, 10%, you need to sample less than 10% of both populations. So essentially the same exact conditions, just twice. Otherwise, you need to have an independent for both. And I will say it's not going to be a mix and match situation, at least as far as I've seen. if you are checking 10% condition, you are checking 10% condition. If you are saying that the population is normal, they generally say both populations are normal. They don't make you do like central limit theorem for this and then say the population is normal for that. So it's usually just one way or the other. But a lot of the time, the random assignment and the independent statements will go together because those are both directly related to means or to experiments. So conditions, check. Other than that, everything else stays the same. We calculate a mean, we calculate a standard deviation, and we keep going. So let's do our last one. And I drag you through this and we write them out because I find that if I don't model it myself, I will have people who don't do all of the steps. And I write this 4 times over again and over and over again. So I do it because I want you to do it. I want you to see that these are all of the parts that have to be there. Every single response that I write, I typically don't have any fluff. I don't put anything in there that's like, oh, well, you don't actually have to say this. The only thing at this point is the first probability statement you don't need, but I do think it's helpful. So whenever I write my responses out, they are what you should be writing on your test. So we have a study is conducted to compare the effectiveness of 2 study techniques immediately, probably 2 populations. They then tell me A and B. Again, another good sign is 2 populations. For technique A, they have a random sample of 80 students, an average score of 85 with a standard deviation of 10. And technique B is a random sample of 100 students. That immediately, 2 populations. As soon as I see that I have 2 means, we have 2 populations, and they're giving me an average and a standard deviation. So we're dealing with means. A random sample of 100 students yields an average score of 82, standard deviation of 8. Calculate the probability that the difference in the average scores between technique A minus technique B. So this is a question that is specifying how they want you to subtract. And I told you, for the most part, you get to choose, but if they tell you to do A minus B, you do A minus B. And they want to know the probability that this subtraction is greater than 4. Now, one thing I will clarify again, you don't have to do 2 probabilities for 2 populations. This one only wants A minus B to be greater than 4. If they had just said they want a difference of 4, then yes, we would do what we did for proportions. We would find both directions. But if they only give you one direction that they want, that's the only one you have to find. So mean score of students using, and I'm just going to use Tech A. We'll just say Tech A to shorten technique. Mu B, mean score of students using Tech B. And they identify what they want me to find. They want me to find the probability that XA bar minus XB bar is greater than 4. Now, conditions, just running down the line. Remember, we have to do it for both. Order does not matter as long as they are all there. That's what's important. So I'm going to have a random, and a little note. You cannot just say SRS. I know people want to use that as an abbreviation for random sample. SRS is a type of sampling. If they don't say that they took an SRS, you don't know if they did a cluster sample or a stratified sample or what. So if they don't say it, you don't say it. So random sample of 80 Tech A students and 100 Tech B students. And for this, we are going to calculate our mean, mu of XA bar minus XB bar is going to be equal to their difference. So their A had a mean of 85, B had a mean of 82, so my average difference is 3. And then we run down the line, normal. A lot of people prefer this normal condition to the one for proportions because it's a little bit less writing. 80 is going to be greater than or equal to 30, and 100 is going to be greater than or equal to 30. So CLT applies, which or says or because of CLT. As long as you mention CLT somewhere, they are going to count it on the AP exam. This tells me that the sampling distribution of XA bar, let's capitalize it since I did that, XA bar minus XB bar is approximately normal. And for independent, we are going to go in and check 10%. And most of the time, 10% is going to pass. So I'm going to be safe to assume that there's enough Tech A students in the population to make sure that this works. Maybe Technique A is they listen to music and Technique B is they don't. So we're just going to go with it. Again, the only time this will truly fail is if they in the question specify, like, my population size is only 10 people, then what can we do? So safe to assume. And then we can calculate our standard deviation. So standard deviation of XA bar minus XB bar is equal to the respective standard deviations over the sample sizes. Now, the one thing that you do have to be careful of is that you have to include the variance, which is why each of those standard deviations that I have are being squared. So 10 squared over 80, 8 squared over 100. Even when you are subtracting for standard deviation, you are always increasing your variability. So that is why in the standard deviation formula, it's never subtracting. It's always adding. So 1.3748. Now, I have my mean, I have my standard deviation. I know it's a normal distribution, so I'm just going to say Z is equal to, the interested value is 4, so I'm going to do 4 minus 3 over 1.3748. This step truly does not change from one population. It's the same exact thing because Z-score is just a standardized score. Probability that Z is greater than 0.7274, which is equal to the normal CDF. Lower this time because I want a greater value is 7274. Upper is infinity, mean of 0, standard deviation of 1. And that's going to be 0.2335. Final step is to conclude the probability that, and I try my very best to just repeat the question so that I cover what I need. Now, if the question doesn't have context, you must write context, so go back and read a little bit more. Average test scores between Tech A minus Tech B is greater than 4 is approximately 0.2335. Now, before I open up the math lab, there's only a math lab today because you got your test review. And there are